So, good morning to all of you. In this lecture, I am going to discuss the concept of cyclic coordinate for a given Lagrangian expression. If we have a Lagrangian profile which is 1 by 2 m r dot square plus r square theta dot square plus z dot square minus mgz. So, this is the profile of Lagrangian. So corresponding to this Lagrangian profile, we have to find out the cyclic coordinate, or we have to check whether the cyclic coordinate exists. If it is exist, then in which coordinate corresponding to whether this system whether it is cyclic in r or theta or in z coordinate system. In previous lecture, I have already discussed the concept of generalized momenta corresponding to same Lagrangian profile. We know generalized momenta is basically del L upon del QK dot, which is PK. In this case, we will check cyclic coordinates. So to check the cyclic coordinates, we need to simply check mathematically where. So for a cyclic coordinate, check del L upon del QK is equal to 0. If this del L upon del QK is equal to 0, which implies that our del L upon del QK dot is simply PK dot, which is constant. We have already derived this relation from Lagrangian equation of motion. So from Lagrangian equation of motion, if del L upon del QK in Lagrangian equation of motion, if you will put del L upon del QK is equal to 0, then del L upon del QK dot is PK, which is constants. So this is the concept of cyclic coordinate. It means momenta corresponding, if cyclic coordinate exists, which means corresponding momenta is conserved. So let us evaluate, or let us check the cyclic coordinate corresponding to r, theta and z coordinate, because our QK is, in this case, our QK, because we have a Lagrangian profile which is 1 upon 2 m r dot square plus r square theta dot square plus z dot square minus mg z. This is the Lagrangian profile, and simply Lagrangian is T minus V. So this one is kinetic energy and this mgz is potential energy. So this is a Lagrangian in cylindrical coordinate and this is mgz potential, having potential mgz. Now our QK, what is our QK? Because for cyclic coordinate we need to check whether del L upon del QK is 0 or not. If it is 0, then corresponding coordinate is cyclic coordinate. So what is our QK? Here QK is simply r, theta and z. So we have to check from here that we need to check what is our del L upon del r 0, del L upon del theta 0 and del L upon del z 0. If del L upon del r, del L upon del theta, del L upon del z all are 0, then we have a cyclic, then our system or our dynamical system having cyclic coordinate in r, theta and phi. If it is not 0, then there is no cyclic coordinate, which means the corresponding, there is no constant of motion, which means there is no corresponding momenta is conserved. So corresponding momenta, if it is 0, then corresponding momenta is conserved. It means PR is constant. It means P theta is constant. It means Pz is constant. So this is the physical meaning of cyclic coordinate. If our del L upon del R is 0, then PR is conserved, constant. If del L upon del theta is 0, then corresponding P theta is constant of motion, conserved. If del L upon del Z is 0, then corresponding Pz is constant or constant of motion, and corresponding momenta is conserved. So let us check it one by one. So for r coordinate, del L upon, what is our del L upon del r? So del by del r, now putting the value of L, which is 1 upon 2m r dot square r square theta dot square plus z dot square minus mg z. This is the value of L. Now putting the value of L in order to find out the value of del L upon del r. So del L upon del r, this is partial differential equation, because our Lagrangian equation of motion is a simply second order partial differential equation. So this is del L upon del r is differentiating partially L with respect to r. This is the meaning of del L upon del r, differentiating partially L with respect to r. So if we are differentiating partially with respect to r, which means treating rest of the variable as a constant, and differentiation of constant is 0. So what is the del L upon del r corresponding to r dot is, because this is r dot and we are differentiating with respect to r, so this will definitely give us 0. This will give something because we have a profile of r, so this will give r, and this is z dot, this will again give 0, and this will give something. Sorry, this will again 0 because this is z, we are differentiating partially with respect to r. So now taking 1 by 2 m outside, del L by del r with respect to r dot is 0, del L by del r corresponding to this will give 2r theta dot square plus 0 minus 0. So we have this 2 will cancel out, and we have mr theta dot square. So what is profile of our del L upon I? So del L upon del r is simply mr theta dot square, which is not equal to 0, which means there is no cyclic in r, our dynamical system or this Lagrangian system is no cyclic in, there is no cyclic coordinate corresponding to r coordinate. So no cyclic in r, which means if it is no cyclic in r, which means PR is not conserved. It means PR not conserved, or there is no constant of motion corresponding to r generalized coordinates. So no constant of. Now similarly for theta coordinate, we need to check whether our del L upon del theta is 0 or not. So del L upon del theta, again 1 by 2 r dot square theta dot square plus z dot square minus mg z. Now again differentiating this partially with respect to theta. So there is no theta coordinate. We have theta dot coordinate, but there is no theta coordinate. So this will give 0. So del L upon del theta is 0, which implies that cyclic in theta. So this Lagrangian system or this dynamical system is cyclic in theta, which means P theta is constant. P theta is constant. Means angular momentum is conserved, which means P theta, what is PR is linear momentum, but P theta is angular momentum. So this again implies that angular momentum corresponding to this dynamical system is conserved. Now let us analyze the z coordinate. So for z coordinate, del L upon del z, which is del by del z 1 by 2 m r dot square theta dot square plus z dot square minus mgz. So this all will give 0 because this is differentiating partially with respect to z and treating rest of the variables are as a constant. So we have only z profile in mgz in potential. So this will not equal to 0. This will give something, and what is this is simply 1 by 2 m minus mg. No, this will 0. So we have simply mg. So del L upon del z is minus mg, which is not equal to 0. So we can say that no cyclic, the given dynamical system, no cyclic in, so there is no cyclic coordinate in z coordinate system. So we have only one cyclic coordinate, that is in theta. So we can summarize that del L upon del R is not equal to 0, del L upon del R not equal to 0. So no cyclic in R. Del L upon del theta is equal to 0. So del L upon del theta is 0. So this is then Lagrangian is cyclic in theta, which means corresponding momenta is conserved, which means angular momenta is conserved, and del L upon del z again not equal to 0. This del L upon del z not equal to 0, which means no cyclic in z coordinate. It means corresponding momenta pz not conserved. So there are n number of ways through which one can ask questions, because so this is a very complex profile of Lagrangian. So corresponding to this complex profile, we can find out the different parameters. We can evaluate del L upon del theta, del L upon del R, del L upon del z, and corresponding momenta. So we can find out generalized momenta and cyclic coordinates. So corresponding to this Lagrangian, we have only one cyclic coordinate, which is in theta, and there is no cyclic in, so there is no constant of motion in R and Z coordinate system, but there is a constant of motion in theta coordinate system. So this is the way to analyze the concept of generalized momenta and cycling. In previous lecture, I have already discussed the concept of generalized momenta and how to obtain the expression of generalized momenta for a given Lagrangian. In this lecture is only focused on the concept of cyclic coordinate, that what is cyclic coordinate, what is the physical meaning of cyclic coordinate, and how to evaluate or how to obtain the expression of cyclic coordinate, or check whether the given Lagrangian is in having a cyclic coordinate or not. For a given Lagrangian, how to check the given dynamical system or given Lagrangian having cyclic coordinate. So it's all about the cyclic coordinate, which is simply del L upon del qk is 0. If it is del L upon del qk is 0, it means there is cyclic in qk. This qk could be anything. In this case, our qk is r, theta and phi. So it's all about this example. Thank you.